Alright, get ready. We're going to explore the predator-prey model now in a whole new different way using what's called Nullclines. First, I'll give you the predator-prey model, which we've talked about a lot of times. We'll just go over the terms to make sure that we understand what it means in context. N is going to be representing the prey, and so like any good prey, hopefully in the absence of any predation, that type of animal would grow exponentially with some continuous growth rate. When that animal interacts with the predator, which is labeled as P, the interaction is going to be modeled as a product of the two populations, and the term here is going to be negative for the prey because it's detrimental to the prey, and it's going to represent how efficiently the predator is catching the prey. P prime is going to be the equation for the predator, and in this type of modeling, we assume that in the absence of any prey to eat, the predator is going to die out exponentially because it doesn't have any food source. Interactions with the predator are still modeled with that product, and you're going to see that this number here is always less than this number because really what's going on is that this whole term, including the 0.01, is going to be multiplied by another term that speaks to how efficiently the predator is processing the prey. So catching the prey and then times another term that illustrates processing the prey. Okay? And what we're going to do with these equations to aid our work is that we're going to try to write them in a factored form because we're going to be analyzing the nullclines, which are the locations where one or the other equation is set equal to 0 independently. Okay, that's going to be easier if we have factored forms. So for the prey equation, I factored out the common term of n, and for the predator equation, I factored out the common term of p. All right? Nullclines are places where the differential equation is set equal to 0, but just for one specific variable, not for both variables at once. Once we figure out the nullclines and then we graph them, the places where the nullclines intersect are going to be the places where both equations are equal to 0 at the same time, and those are going to represent the equilibrium. So the n nullclines represent the places where the dn dt is set equal to 0. Because it's in factored form, I can just cleave off each individual factor. So either n will be 0, that's where I get this nullcline, or this quantity inside here is going to be equal to 0, and that gives me, solving for p, the other nullcline. For the p nullclines, we do the same process for the dp dt equation, and so this factor equal to 0 would give me this nullcline, and this factor in parentheses equal to 0, solved out for n, is going to give me that nullcline. Okay, so let's just start the process by graphing the nullclines. Here I'll be using blue for the n nullclines and p for the red for the p nullclines. Okay, so first I want to graph n is equal to 0. Here's the n axis, and this is the place where n is equal to 0. So n is equal to 0 represents a vertical line, which technically should be right on top of the p-axis. I'm just drawing it to the side a little bit just so you can see it separately than the p-axis. But this represents the vertical line at n equals 0. The other nullcline there is going to be p is equal to 0.4, and the p is a vertical axis, so p is equal to 0.4 is going to be at some level right around here. Okay? So those are the two n nullclines. And now in red, I'm going to draw the p nullclines. Where did I put the red pen? Oh, there it is. Okay, so I got the red pen here, and I'm going to draw the p nullclines. P is equal to 0 is the first one, and that's going to be a horizontal line, which would be right on the n-axis, but again, I'm just going to draw it a little above just so you can see it. And then the other one is n is equal to 20, and that's going to be all the way over here. I'm not really going to be able to draw this to scale because this is equal to 0.04, and this is going to be my level 20 here, so this isn't exactly to scale. I would encourage you to also type this into the vector field plotter so you can really see what it looks like to scale. And if you do that, make note that your n-axis is going to have to run from 0 all the way past 20 to be able to see that. But then your p-axis doesn't really need to go up all the way to 20 because the other line of interest here is at 0.04. So I would recommend that you do maybe p from 0 to 1 and n from maybe like 0 to 25 or something like that. That way you'll be able to capture the points of interest. What are the points of interest? Well, for this, we want places where both dn dt and dp dt are both going to be equal to 0. And so that visually corresponds to places where a red line is intersecting a blue line. Remember not to get tricked. If a blue line is intersecting a blue line, that doesn't count. Because where blue intersects blue is a place where just n prime is equal to 0, but p prime isn't equal to 0. Likewise, red intersecting red over here, that doesn't count because that's just satisfying the p prime is equal to 0 equation, and it doesn't also satisfy n prime. So we need them both satisfied at the same time, simultaneously, in order to yield the equilibrium points. There's going to be one equilibrium point right here at 0, 0, and then there's going to be another equilibrium point right here. So I'm going to label the equilibrium points with the values here. And this one is 0, 0, and that would represent extinction of both of the species. And this is an equilibrium point where both species exist. And for this, n is going to be equal to 20, and p is going to be equal to 0.4. Remember that oftentimes in population models, the variables are not just the number of animals, but the units might be hundreds or thousands or millions of animals. And so a lot of times, even though we have fractional values for the population levels, it still makes sense in context when you look at the units. Okay, so far we've solved for the Nullclines by setting the differential equations equal to 0 separately and taking advantage of the factored form, so we can just use each of the factors separately. And then we also located the equilibrium points by finding places where the one color intersects another. Expert tip: always draw Nullclines using different colors. Use one color for the first variable and use a separate color for the second variable. If you don't use different colors, you're probably going to get tricked by the blue versus blue, and where the red crosses red lines, you won't be able to know. So really use that. Make sure that you use different colors for the two variables. Okay, now why do we bother with Nullclines? That's because it gives us a really good feel for the vector fields. And as we get into more advanced topics such as bifurcations, we're going to use that more in-depth understanding of how the vector field is related to these Nullclines in order to talk about how different changes in the parameters might change the overall behavior of the system. Okay, so this is a very useful technique. Sometimes at first it kind of feels like, what's the point? But trust me, there's definitely a point, and it really aids our analysis of the qualitative behavior of differential equations. Okay, so hopefully you're just trusting me on that. Now we're going to draw some arrows on the Nullclines. This is typically a very confusing thing to do. I'm going to try to go through it as slowly and clearly as I possibly can. But I just want to say that right off the bat so that when you start to feel confused or frustrated, know that it's very common. I've been there lots of times, and this is hard. This is going to be hard, so let's just get to it, but know that it will be challenging. Okay, so what we're going to do is we're going to try to describe how the vector field behaves on the Nullclines. Now, I know I just said that Nullclines are places where you set the differential equation equal to 0, but remember that in 2 dimensions, this is a technique for 2 dimensions, the vector field has 2 components. It has a horizontal arrow component and it has a vertical arrow component. Okay, this is 2 dimensions. So when I look at the blue Nullclines here, the n Nullclines, what it's telling me is that on the n Nullclines, dn dt equals 0. So on the n Nullclines, dn dt, I know for a fact equals 0 because that's how I got the n Nullclines, was I set this equal to 0 in order to get that. So what that means for our visual in the state space is that dn dt represents the horizontal component of the vector field. dn dt tells us if the vectors that we overlay on top of the state space are going to be pointing to the right or pointing to the left. And because we know that dn dt equals 0, there's no left or right behavior left. But it doesn't say that dp dt equals 0 on the end nullclines. In fact, it usually doesn't unless you're at a fixed point. And so what I'm trying to say here is that on the end nullclines, the vector field has only vertical, and that's up or down, component. Only a vertical component. Okay? So that means that when I try to graph the vector field at a point which is on a nullcline, if it's on a blue nullcline here, it's not going to point left or right at all. It's only going to point up or down. The same is true in the opposite way of the red places. On the red nullclines, there's going to be no up or down behavior. There's only going to be left or right. And so, I know it's a little confusing, but what I'm going to do right now is I'm going to take the red pen. The red pen is representative of the vertical or P component of the vector field, and I'm going to use it to draw up or down arrows on the end nullclines. Because the end nullclines, they don't have any left or right going on. That's what this says right there. They only have up or down. If it's up, it's because P prime is positive. If it's down, it's because P prime is negative. So I have to figure out the value of P prime on the end nullclines. That's what I'm trying to do. Okay, so now I'm going to look at dp dt on the end nullclines. Okay, and so the first end nullcline I have is n is equal to 0, right? So that's my nullcline, n is equal to 0, but what I'm going to do is I'm going to plug this statement into the equation for dp dt to see if I can determine whether it's pointing up or pointing down. Okay, so I'm going to look at p prime, and p prime is equal to 0.01 times n times p, 0.01 times n, which is 0, times p, and then minus 0.2p. Okay, so here I'm just copying down the statement of the p prime equation, but I'm replacing n with 0 because I'm going to look at it on the n equals 0 nullcline. Okay, and so that actually simplifies it quite a bit because a 0 right there makes this whole thing 0, and so p prime is equal to negative 0.2p. Now, because p represents a population, it can't take on any negative values contextually, and so I know that p prime is less than 0. On the nullcline, n is equal to 0. Okay, so this is the first conclusion that I'm drawing about the behavior of the vector field on the nullcline for n. Remember, p prime represents up and down behavior, and so if it says p prime is less than 0, what I'm going to do is I'm going to draw the vector field. I'm going to draw it in red because it's an up or down component, but I'm going to draw it on the end nullcline because that's where I'm doing my analysis of the vector field. It would be really hard for me to just draw the whole vector field. That would be magical. That's what we have computers for. For me, as a human, I really have to just pinpoint one little space to work in at a time. And I'm trying to say, I'm just going to work right here on the n is equal to 0 line. Okay, so I'm zoomed in right now on the n is equal to 0 line. And my conclusion is that it only has a vertical component, and that vertical component is always negative. And so what's happening on the end nullcline is I have downward behavior. Always having that downward behavior along the entire n is equal to 0 nullcline. So I've got all those red lines pointing down because that's the vector field pointing down. Okay, I'm going to do that again now, but now I'm going to consider the behavior on the other nullcline for n, which is p is equal to 0.4. All right, I'm going to do the same thing that I was doing before, knowing that I'm going to get strictly vertical behavior and see if I can determine whether that vertical behavior has a positive sign pointing up or a negative sign pointing down. So now I'm going to consider the nullcline p is equal to 0.4. Remember that this is still a blue nullcline that I'm considering. And what I'm going to do is I'm going to look at the equation for d p dt, or p prime, and it says 0.01 np minus 0.2p. Okay, and I'm going to plug in my assumption, which is that I'm on the nullcline. Now I'm on this horizontal line right here. Okay, and I'm going to plug it in for p because it's a statement about p. Everywhere I see a p, I'm going to type that. I'm going to put 0.4. Okay, I'm able to do that because I'm assuming that I'm just looking at this one horizontal line. Okay, so now I'm going to try to simplify it. So it says p prime is 0.004 n minus 0.08. Not as easy as the last one, but it just has an n in it. And so really the sign of p prime is now going to depend on n. And so I can see that if n is really big, like if n was like 1,000,000, then of course this positive term would be greater than that negative term. And so it would be positive or pointing up. If n was really tiny, like if n was just like 0.1, then this term would be less than that term, and so I would get a negative amount, and so the vector field would be pointing down. So that didn't happen to us last time. Remember last time we just drew the conclusion that it was always pointing down? But along this line it actually makes a flip. Sometimes it's pointing down, sometimes it's pointing up. Kind of depends on what value of n you have. So now we have to figure out where it makes that flip. When something changes from negative to positive or positive to negative, it always goes through 0. 0 is the dividing line between positive and negative values. So now I'm going to set this equal to 0 just so I can figure out where the dividing line is between it pointing down for little n and pointing up for big N. Okay? Oh wait, you know what? If I set it equal to 0, you know what I'm going to get? I'm going to get n is equal to 20. Right? Because then they're both going to be equal to 0, right? That was a place where dn dt equals 0 and dp dt equals 0. So I kind of already know the answer, but in case you want to get some proof of that, you would just solve this. You would just set that equal to 0 and bring the 0.08 to the other side. Then you would divide both sides by 0.004, and you would get the conclusion that n is equal to 20 represents that place right there where both different equations would equal 0, right? So this is the dividing line, and it divides the behavior into two different categories. So what I'm really saying here is that p prime equals 0 when n equals 20, right? But p prime is greater than 0 when n is greater than 20, and p prime is less than 0 when n is less than 20. Okay? So this now is the conclusion that I'm getting for the second n nullcline. It's a bit more complicated of a conclusion than the first nullcline, but it does kind of align with what I see here, because I see that there's an intersection point, there's a fixed point or equilibrium point right here, and so it's no surprise that I see a switch in the behavior because 0 makes things switch from being negative, in this case that would represent down, to positive on the other side representing up. Okay, so at least it aligns with what I'm kind of expecting from that. And the final thing that I'm going to do is I'm going to take my red pen that's going to draw vertical components of the vector field. And on the blue line, on the blue nullcline, I'm either going to draw up arrows when p prime is positive, or I'm going to draw down arrows where p prime is negative. Okay, so right here's the level where n is equal to 20. I'm going to use a statement that when n is less than 20, p prime is less than 0 to draw down arrows. See, so I know that if I evaluate the vector field on the n nullcline along this, it's going to be down. Right here, it hits 0. And then on the other side of the line, that's what this statement says right here, on the other side of the line, it's going to be positive. So I would draw a bunch of up arrows like that, going up. Okay, so that is how you draw the little up and down arrows on the nullclines. We just went through the end nullcline, and now we have to do that all over again for the p nullclines. I know this seems tedious and possibly pointless because you have technology, but this is an advanced topic. And if you do move on to really advanced work in analyzing differential equations, you would need to aid your analysis by knowing the behavior of the nullclines in your head. And that's because we want to analyze systems without having put any of the values on the parameters. So I'm just trying to motivate you a little bit because I know this is confusing. But imagine a world where this just had alpha, beta, gamma, sigma, or some kind of, some kind of letters instead of numbers here. I wouldn't have been able to do a lot of this number crunching without any numbers. And then I would just have to use my own logic and reasoning and figure out how all these things behave in terms of the parameters. That's what I mean by the more advanced work requiring your understanding of nullclines. Okay, so now let's go on to the p nullclines. And we're going to see what kind of arrows we're going to draw on the red lines with the blue pen. Okay, and that's because the p nullclines are in red. So on the p nullclines, we know the statement that p prime is equal to 0. That's right. That's how I got the p nullclines, was I set that equal to 0, right? And because p is the vertical axis, that means there is no vertical component to the vector field. So there's no up and down on the vector field. Okay, as long as we stay on the p nullclines, there's not going to be any up and down. But what we're going to see is we're only going to have left or right. We're going to have left if dn dt is negative, that's going to point to the left. If dn dt is positive, then it's going to point to the right. Okay? And so we're going to analyze each of these red nullclines one at a time, but we're going to be using this equation as opposed to that equation. Okay, so let's get started with analyzing what the vector field looks like on the red lines by using the blue pen to represent left and right behavior, because there is no up and down behavior on these red lines because they're the p nullclines. Okay, so we'll just start with the first more simple p nullcline, which is p is equal to 0. And remember that what we're going to do to analyze the vector field is that we're going to plug in this assumption into the non-zero differential equation. If you get confused and you plug in the assumption of this nullcline into the wrong equation, so you try to plug it into p prime, you're just going to get p prime equals 0 because that's where it came from. So it's kind of an easy mistake to correct. If you find yourself doing this work and you're taking a nullcline and then you're plugging it into something and you get 0, you picked the wrong thing to plug it into. For one of the things that you plug it, if you take this and you plug it into one of the equations, you're going to get 0 because that's where it came from. And then if you plug it into the other equation, that's when you're going to get the information that you're looking for. Okay, so I'm taking a p nullcline and I'm plugging it into the n prime equation, which is 0.04n minus 0.1np. And I'm just going to plug in the assumption that p is equal to 0, which results in this, 0.1 times n times 0. And so it just says n prime is equal to 0.04n. Kind of like with the easier one that I started with on the last set of nullclines, this is a statement where when I acknowledge the fact that n is always going to be a non-negative number, then I know that this is always going to come out positive, or 0 at the equilibrium point. So my conclusion is that n prime is greater than 0 on the p is equal to 0 nullcline. Okay, remember, n prime is left and right behavior. And so what I'm going to do is take my blue pen that is supposed to represent left and right behavior, and I'm going to, which way should I point it? To the right. Yeah, because it's greater than 0. And where should I draw all those arrows that are pointing to the right? On the nullcline that I started this out with, right? Because I started here, and then I went through the analysis. And so here's the nullcline that represents p is equal to 0, and I would just say that it's always going to the right, so it's always going this way. Okay, and really that vector field behavior is right on top of the nullcline. I just didn't want to mix up the pen coloring, so I kind of drew it on top of it. And, but all this stuff is happening right on the line p is equal to 0, so right on the n-axis is where that type of to the right behavior is going on. Okay, so we just have one more to do. We just have this vertical line that represents the second p nullcline. And so we're going to go through this process again. This one's going to be a little bit trickier, so I'm going to need more board space. And I'm going to take the second p nullcline, which is n is equal to 20, and I'm going to plug it into the equation for dn dt, right? Okay, because this is a p nullcline. And so n prime is equal to 0.04 n minus 0.1 np. And now, using my assumption here, I get 0.04 times 20 minus 0.1 times 20 times p. And let's see, that's 0. Geez, I should have done this out. Minus 0. Or this is going to be a 2, I think. 20 times 0.1 is 2p. Okay, so I got the statement that n prime is equal to 0.8 minus 2p. I can't really say that for sure that's negative or for sure that's positive, because I can tell that if I have just a little teeny bit of p, like if p was equal to 0.01, this would come out positive. But if I have a really big p, like p is 100, then that's going to come out negative. I'm kind of doing the method of test points in my head right now. That's what I'm doing when I'm describing that. Just like before, we're going to have a flip-flopper, where sometimes we're going to be going to the right, sometimes we're going to be going to a left, and the dividing line between positive and negative is still going to be 0. So I'm going to set this equal to 0 just so I can see where the dividing line is. And if I do set that equal to 0, you're going to see that the conclusion is p is equal to 0.4. That's okay with me because that is the other nullcline, right? And remember that the intersection of these two places represents the fixed point right here. And so I'm kind of doing a double check, confirming that I'm on the right path when I get that the dividing line is indeed the equilibrium point. That's a general statement. If your vector field behavior is going to make a switch on a nullcline, it's because it passed through an equilibrium point. That's always true. Continuous functions can't change from positive to negative without passing through 0. So we keep implementing that piece of analysis as we go through this. Okay, so here's a dividing line. N prime is equal to 0 when p is equal to 0.4. Okay? So when p is less than 0.4, I'm just going to do a little imagination here. If p is a really tiny number, then I'm going to get something that's pretty much positive, right? And so n prime is greater than 0 in that case, and then n prime is less than 0 if p is greater than 0.4, and this is my conclusion for the second p nullcline, the line where n is equal to 20. Okay, now, on a p nullcline, we just have left and right, and so I'm going to use my blue pen, and I'm going to draw to the right in this case, and I'm going to draw to the left in this case. Okay, and here you can see that this was the line of 0.04 right here. And so what I have here is it's to the right this way, and then it goes to the left for everything up here. Oh, wow. I'm really filling out this vector field. And actually, check out the description of this video because I put a link to an already prepared phase plotter where I already typed these equations in, and you can confirm everything that you're seeing here with that link. So that's a little bonus. You might just have to change the axes, like make sure you go from 0 to something past 20 here, and make sure you don't go too high up here, maybe 0 to 1 is the best to see the window. Okay, so I'm just going to take a step back and look at what I've learned so far. What I have done is analytically derived a whole bunch of information about the vector fields, And what it's kind of telling me is that these nullclines are breaking the state space up into different regions. And that, again, is a general statement, is that nullclines are going to break the state space apart into regions of qualitatively similar behavior. Okay, so now I'm going to draw some parts of the vector field that are off the nullclines, and I'll just use my black pen for that because these are going to have vertical and horizontal components mixed together. And I'm going to talk about the 4 different quadrants that I've broken it into. There's 4 quadrants basically because I have this crosshairs here, and then these are pretty much just the boundaries over here. Okay, so in this big quadrant here, it tells me that stuff's going to go to the left, and it's also going down. Now on the nullclines, it's exactly just going to the left on the P nullcline, and exactly just going down on the N nullcline. But in the region that's not on a nullcline, there's going to be some combo of to the left and down. So it's going to look like this. In different ways. You know, there could be different combinations of it, and really I couldn't figure out exactly what these vectors look like by picking a point, right? Like let's say that I picked a point like this where, I don't know, maybe n is equal to 5 and maybe p is equal to like 2. And if I picked this point in the state space and I plugged in 5, 2 into these equations, I would get a vector that has a negative horizontal component and a negative vertical component. Okay? Go ahead and practice that if you want a little review of evaluating vector fields, which we learned back in chapter 1. That's a good practice. The whole quadrant's like that. That's the magic of the nullclines, is that back when we very first learned about vector fields, remember how tedious it was to like pick points one at a time and then figure out what the vector was and draw it and then pick another point, pick another point? Well, you've made it so far that now you're talking in big generalities. And so what I'm saying is that because I know the nullclines are cleaving off this area as an area of qualitatively similar behavior for the vector field, I know all the vector field arrows are pointing down and to the left in that region. That's pretty cool, right? It's worth it. So let's go into the next region. Okay, so this region in here says I'm going down and I'm also going to the right. And so it's going to be some combination of down and to the right. So vectors in this region are going to kind of look like this. A combo of down and to the right. Okay? In this region over here, we're talking about going to the right, but also going up. And so it's going to be going to the right, but going up like that. And then finally, in this 4th region over here, they're going to be going up, and they're going to be going to the left. And so they're going to be looking like this in this region. Again, they're not all going to have exactly the same slope on the vectors. There's a lot of different ways that I can go up and to the left at the same time, right? I could do that really steeply, or I could do that really shallowly. So I'm not saying that all these vectors have the same angle. If I exactly wanted to know exactly what those vectors look like, I would probably use technology at this point. Or I would find myself doing a bunch of this for different test points all over the region. Yeah, so definitely look at that link because I got the vector field up for you there and it looks really nice. Actually, you can kind of see from all the work we've done so far that you've got this swirling behavior, this counterclockwise swirling behavior. And if you remember, throughout this course, studying the predator-prey model, we have that cyclic behavior where trajectories make perfect closed loops around the fixed point. This is a very special model. I would say it's not exactly ecologically like realistic because you have those perfect closed loops, but it does match up with observations, real data-based observations from field ecology quite well. And so it's surprising how much we can do with such a simplistic model. So here we have now derived, through our analysis of nullclines, how we get that counterclockwise, cyclic, closed loop and periodic behavior in the predator-prey model. Cool.